Static gesture recognition for Indian Sign Language alphabets and numbers using SVM with orb K points and image pixel as feature. Abstract: sign language is used by deaf-dumb people to communicate with each other. They cannot communicate with normal people as normal people do not understand sign language. To bridge this gap, there is a need for a communication medium. The sign language recognition problem belongs to the gesture recognition domain. There are two types of signs, static and dynamic, respectively. The given study covers the methodology for recognition of static signs. 35 classes includes 26 alphabets and 9 numbers, of Indian Sign Language, ISL. The work aims to fulfill the fingerspelling application by recognizing alphabets and numerals of ISL. The SVM is used to classify different characters of Indian Sign Language. There are two feature extraction approaches discussed in this paper. In the first approach, an image is used as a feature to feed the classifier, and in the second approach, the orb K-point based feature extraction method is used to train the classifier. The trained models stretch to predict the ISL sign images taken under the real-time, uncontrolled, situation. Keywords: Indian Sign Language, static gesture, SVM, orb K-points, image pixel as feature. Introduction. Spoken language is used as a medium of communication between normal human beings. Without spoken language, it would not be possible for a large population to communicate. Even with the existence of spoken language, a part of the population with speech and hearing disabilities cannot communicate with the majority of the people. Sign language comes to the aid of such a community. Deaf-dumb people use sign language as a mode of communication. But they face problems while communicating with normal people because they do not have prior knowledge of sign language. In many cases, a human translator is available who translate the sign language to a normal human understandable form. Still, the availability of a human translator is not feasible every time. Sign language is well structured, and every sign gesture has a meaning. Sign language has its alphabets, numbers, and rich set of word dictionaries. Sign language uses hands, movements of hands, and expressions to represent the alphabet, number, or dictionary word 1. Sign language recognition is the problem that belongs to gesture recognition. Broadly, the gestures are static and dynamic, respectively too. Static gestures are used to present signs with the stable hand/s without any movements. There are non-dictionary words like a person's name, things, etc. where alphabets and number recognition play a significant role. The given study covers recognition of static gestures of Indian Sign Language, ISL, i.e. alphabets and numbers using SVM. The alphabets and numbers use either one hand or two hands to represent particular sign characters. This set of characters belongs to the category of static gestures too. The dataset used in the study has different 35 classes of ISL characters, 26 alphabets and 9 numbers of ISL. For each class, there are 1,200 images captured and stored. There are 42,000 images available in the dataset for different 35 classes 3. All the ISL alphabets and numbers are given in Figure 1. 2. Related work. In this section, various techniques and approaches are discussed which used by researchers to recognize static gestures of ISL. Sagenridge et al. 4 present a technique to recognize the numbers of ISL using the deep learning technique, CNN. They have achieved 99.56% accuracy for the same subjects and 97.26% accuracy in low lighting conditions. Asood et al. 5 works on static gesture recognition where they have used Harris algorithms for feature extraction. Viaditya et al. 6 present the work on recognition of 36 different characters, 26 alphabets, and 10 numbers for fingerspelling. They have used shape feature derived from the distance transformation of the binary image and used AN as a classifier. They have achieved an accuracy of 91.11%. R.K. Shangeetha et al. 7 presents a technique to recognize single-handed gestures where the state of a finger is used to identify the sign. They have selected the features like the angle between fingers, number of fingers fully closed, semi-closed or fully opened. S. Chattaraj et al. 8 have used a scale invariant feature transform SFIT, algorithm for feature extraction. S. Rishna et al. 9 present a technique to recognize 11 static symbols using Hogg features with SVM as a classifier. S. Shinda et al. 10 calculate the angles and the peaks between the fingers to extract the features. They have used a 12-bit binary sequence for each hand gesture, classifying the different hand gestures for classification. Shravani K et al. 3 have used SIFT and SURF feature extractions techniques with Bag of Words model. Idea of BAO is adapted from natural language processing, NLP. In image processing, BAO model concept can be called as histogram-based representation of independent features. So, an image can be viewed as a document in order to depict any gesture using the BAO model. With their approach, all the labels are correctly classified by the SVM except gesture of number 2. 3. Proposed solution. We proposed to develop static Indian Sign Language alphabets and a numbers recognition system. The input to the system is the image of a gesture, and the output will be the text that presents the alphabet or number. The steps include input, pre-processing, feature extraction, classification, as shown in Figure 2. The image is used as a feature in a given study. Further, the multi-class support vector machine, SVM, classifies various ISL characters. A dataset pre-processing. In this experiment, we have used the ISL alphabets and numbers dataset from Shravani K et al. 3. The dataset of ISL contains 35 classes, each class with 1,200 images. All 35 classes comprise alphabets, AZ, and numeric, 1 to 9, with a total of 42,000 images 3. The original dataset of different 35 classes is pre-processed by applying neural network-based skin and non-skin segmentation technique, which we proposed. Each image is taken from the original dataset, segmented skin and non-skin pixels in the image using a neural network-based segmentation algorithm, and stored each pre-processed image in appropriate class folders. The skin and non-skin samples dataset is used from UCI Machine Learning Repository 11. Dataset has a total of 245,057 samples. From total samples, 50859, 21%, are skin samples and 194198, 79%, are non-skin samples. The samples belong to the dataset are red, R, 0 to 255, green, G, 0 to 255, and blue, B, 0 to 255, values of a pixel taken randomly from human face images with labels 1 for skin and 2 for non-skin pixel. The face images of different age groups, young, middle, old, race groups, white, black, Asian, and genders are obtained from Ferret and PAL databases 11. Dataset has 51,444 unique samples, 28% skin and 72% non-skin, and 11 distinct RGB samples out of 51,444 belong to both skin and non-skin classes. Figure 3 shows the sample of each 35 classes before and after pre-processing. As shown in Figure 3, the images in the pre-processed dataset only contain skin pixels, and other pixels are replaced with black. For better feature extraction, such a processed dataset gives better features than the original dataset images. Only skin pixels in an image leads to get good classification accuracy. B. Pre-processing, segmentation. In this stage, all images are pre-processed for feature extraction. The captured gesture image is in RGB format. The image is converted to a grayscale image with a gray level intensity range from 0 to 255. The grayscale image is resized to 128*128 to reduce the processing time and improve the system's accuracy too. The next step is segmentation, in which the neural network-based skin pixel segmentation technique is used, as discussed before. After the segmentation, the skin pixel is available in the image, which represents the hand/s of the signer. See feature extraction. The next step is feature extraction. As discussed in the dataset pre-processing section, the whole dataset is pre-processed for better feature extraction. In the given study, we have examined two approaches for feature extraction. In the first approach, we have taken the whole image as a feature, and in the second approach, there are orb K-points taken as a feature. In approach 1 for feature extraction, we have taken the whole image to train the classifier, where the 128*128 RGB image is converted to grayscale and flattened to generate the feature vector. The 16,384 sized feature vector is generated from 128*128 image. The feature vectors are generated for all the images available in the pre-processed dataset. The 2D array of the feature vector is generated where there are 42,000 rows in the array. Each row consists of two columns where the first column holds the 16384 pixel values, and the second column stores the class label of that image. Figure 4 describes the approach. 1. The approach. 2 for the feature extraction technique is orb K-points based features. Concerning the research by 12, the orb is the most efficient feature detector descriptor with the least computational cost. Other well-known K-point detector algorithms like SIFT and SURF are computationally costly, and they are patented algorithms. We cannot use those algorithms for free. The experiments focused on orb-based feature detection technique. The orb feature descriptor returns the K-points from the image. We can generate the feature using these key points and use the K-points vectors to train the classifier. Different 35 classes of images have a different number of K-points. During the vectorization process, the vector size must be the same to feed the classifier. We found the class with the maximum K-points to solve the feature vector equalization problem. Next, we created the vector space, which stored the orb key point descriptor of the maximum number of K-points and stored the number of total K-points in the image on the last vector element. Now, to equalize the vector in the case of class with fewer K-points, we have padded 0 in the vector with the number of K-points stored at the last vector element. We have generated the feature vectors to feed the classifier by following this method. Table 1 shows the number of K-points for random images taken from the dataset for different classes. As per analysis, the image from class B gives the highest number of K-points. To equalize the feature vector, we have to consider the feature vector size of 200 with padding of 0 after the K-point values, and at the last element of the vector, we have stored the total number of K-points. Figure 5 demonstrates the orb K-points detection for sample images from the dataset. The corners, edges, and blobs in the image are considered as K-points. Figure 5 orb K-point detection. Declassification. 1. Approach one image as a feature. After generating the feature vectors as described in for image as a feature, the next step is classification. It is essential to divide the dataset for training and testing for classification. We have split the dataset 80:20 ratio. Here, 80% of the dataset is used to train, and 20% of the dataset is used to test the classifier. From 42,000 images in the dataset, there are 33,600 images used for training and 8,400 images for testing. We have used Support Vector Machine, SVM, as a classifier. The classifier gives 99.5% accuracy for training and testing the dataset with the image as the feature method. The model gives correct predictions while predicting the class of any image from the dataset. The reference 3 has achieved an accuracy of 99.98%, but their approach does not classify class 2. For the validity of the classification, we have tested the trained model for the different 30 classes images taken under an uncontrolled environment. The model predicts 50% of the images classes taken under an uncontrolled environment. Table 2 shows the results for different 30 classes prediction. 2. Approach 2 orb K-points as a feature. As per the second approach for features, i.e. orb K-points, we have used the orb K-point vectors to train the SVM classifier. As per the previous approach, we followed an 80:20 ratio for training and testing splits. The classifier gives 99.7% accuracy for training and testing on the dataset with the orb K-points feature. For the validity of the classification, we have tested the trained model for the different 30 classes images taken under an uncontrolled environment. The model predicts 27% of the images classes taken under an uncontrolled environment. For results and discussion. By experiments with SVM-based classification, while we have selected the image as a feature and fed the classifier, the accuracy given by the model is 99.5%, and the classifier correctly predicts each image of the dataset. Further, we have provided sign images other than dataset images. In that case, the model predicts 5, 8, C, D, E, F, G, H, I, J, K, L, O, U, and Y class correct, as per Table 2. Character V and 2 have equal orientation, and the model gives wrong predictions in real-time images. The model predicts the sign of character 2 as V. There are certain limitations of approach 1 as shown below. It is non-invariant to rotation and scaled images. This approach may fail if the hand/s in the image is rotated or scaled. The number of features per vector is very high, i.e. 16,384. The larger number of features cost the high computation for the classification process. This approach is sensitive to noise. If the background of the hand region in the image is the same as the skin tone, then the prediction might be wrong. Orb K-point detection is a better feature detection technique invariant to rotation, scale, and non-sensitive noise. Figure 6 demonstrates orb K-point detection and matching with scaled and rotated hands in different images. The K-points are considered a feature, and the number of features is less than the approach 1. The approach 2 results under an uncontrolled environment are not impressive. Approach 2 gives less prediction accuracy than approach 1, but it has more capabilities to overcome the limitations of the first approach. Figure 6 Orb K-point detection for scaled and rotated hand images. V. Conclusion. Indian Sign Language recognition is essential to research for deaf-dumb communication in India. The given research covers the recognition of static signs of Indian Sign Language. The objective of the work is to recognize ISL alphabets and numbers for fingerspelling applications. The different 35 classes, including 26 ISL alphabets and 9 digits, are experimented. We have performed classification using SVM with 2 feature extraction techniques and compared and analyzed both approaches with their strength and limitations. Few experiments are performed on the sign images taken under a real-time, uncontrolled, environment for both approaches. The orb K-point detection is invariant to scale and rotation and overcomes the limitations of approach 1. Orb does not perform better for classification on real-time images than approach -1. Still, we can improve orb K-point based classification accuracy by applying good feature engineering techniques.